Got you with your cream when you're mushing, yeah. Yeah.
So you're standing in front.
I'll get out of the way. Okay, I'll stand over here. Yeah, Look, thanks very, very much, everyone, for coming along. We are very aware of the pressures and so on that are on teachers generally and primary teachers in particular, particularly if you've got family and loved ones at home and kids that you have to run around to sport and all that sort of stuff. So thanks very, very much again for making time to come along. This is the first of what we might run a few of these over the next couple of years as joint enterprises between STAWA and the Einstein-First Project. Dave will talk about the Einstein-First Project a little bit, and so you'll get a general kind of idea of where we're trying to go with it. I am a member of the Einstein-First team, but I'm a volunteer, if you like, as is apparent from the aged appearance. And I'm working with the team, but on behalf of Science Teachers Association of WA. This afternoon, very quickly, the housekeeping, the men's is just the first, as you go out the door, there's first on the left, and the girls is a little bit further on the left. I think that's all. Evacuation, I don't know what happens with evacuation, guys. Here we just head out the door and out into the great court. Is that the drill? We'll make that the drill for today. Okay, hope the occupation is safe and help people out here. Look, we have with us, and this is the first we're trying out, from Pemberton, Alexa, and Carolyn Bradshaw from Adams Road Primary in Bunbury. So I hope you can both hear us loud and clear, and that all the technology behaves itself. On the chairs, there's some bits of paper. We can worry about them later. Don't worry about them now. There's the outline of the program and the detailed notes about David and Malcolm. So I'll just do very brief introductions as we go through those. Introduce each of them. And then there will be hopefully 20-30 minutes towards the end where we can share, and you guys are brilliant at responding to the request for information. The depth of information that we received is really fantastic. But if you haven't had time to do that yet, I sent a link, I think it was yesterday afternoon or maybe the afternoon before, I've forgotten. And there's some quick questions, and we just want a bit of feedback. And then at the end of it, Kyla is going to be able to share that through the Google Doc or whatever kind of sharing document it is on the screen. And we'll make that available, obviously, to everyone here, probably tomorrow once we've had a chance to go through and just edit and get them a little bit more concise. So with those introductory comments, any questions before we start? We're on a pretty tight timeline. We will definitely finish right on 6. I think we'll need right up until 6 to finish. Can I introduce Dave Blair? Dave is Emeritus Professor at the centre here, renowned for his work in gravitational wave research, and was the founder of the Gravity Discovery Centre up at Gingin. Has anyone been there? Yep. Okay, so it's really Dave's vision and missions probably now, and nightmare. So, but it's certainly a wonderful state resource for us. So, and then of late has got involved in the Einstein-First initiative, which he'll talk about. So, Dave, over to you.
Thank you, David. So thank you all for coming. It's a great pleasure to be able to talk to you about climate change. It's really difficult to work out exactly what level to be talking at, but please interrupt and say, if things are completely over the top. Or if you think it's all trivial as well. And I should say, I put quite a lot of stuff together to try to cover all bases, but it means there's some things I'm going to have to just totally skim over, and the PowerPoint's going to be available to you, so that, and I'm hoping that some of it will be useful for you to, maybe use, in the classroom, show other teachers or something like that. Yeah, just make sure I get all this technology right. Down button, not working. Sorry, Carla. Yeah. Oh, right. Good. So I want to start by telling you like a little bit of a story, which is really the history of discovery of things about the climate and the things that are necessary to explain about the climate, and in particular climate change. And I want to tell you a little about tiniest bit about Einstein. As I said, say there, the kid that changed the world and gave us the understanding to save the world. And I'm going to talk about photons and molecules and carbon dioxide. But I'm going to show you at the same time, try and show you the toys and things that we use to make this all completely understandable for young people. And kids always, are full of questions. And our job needs to be to answer their questions and to answer them as so well as we can. And so why does carbon dioxide cause global heating? What sets the temperature of the Earth? Why should we care about tiny amounts of CO2? We hear it's parts per million, and so why should we care? Then I want to say a little bit about technology to stop the Earth getting too hot, and then some stuff on climate history, and that's where I possibly overlap into stuff that Malcolm's doing. And Malcolm, please tell me if you're covering exactly the same ground, because then I can just skip over it quickly. And then about the things that we can be doing. And one of the things I think is important is that kids feel much better about problems if they see that their parents or their teachers are concerned about it and trying to help. So I think if they see everybody's trying to help, they feel much better. And an important thing is not to be giving a sense of despair. And it'd be very easy to do that. So I'm keeping that in mind. But my story starts in Albany in 1801. And it's interesting that you can start a story about climate change in Albany. And it starts with Robert Brown, who arrived in Albany on Flinders boat in 1801. This isn't a picture of him arriving. This is a painting done around that time. But Robert Brown was a botanist, and he had with him Ferdinand Bauer, who was and I think he was an Austrian artist, and he painted all the things that Brown collected. And one of the things that Brown was really interested in was pollen, and he had some of the first microscopes, so he could look at the pollen grains of the plants. He named more than 1,000 species of plants, and he discovered something that took a century to explain, and Einstein explained it, and I'll come to that. But that's the important connection. And there he is, Robert Brown, and there is pollen as seen with modern electron microscopes today. It doesn't look nearly as beautiful with an ordinary microscope. A few years after that, all this is before the Swan River settlement, 1808, Dalton proposed his atomic theory of matter. Now, people had ideas that matter was made of atoms, like Democritus 2,500 years before, but there were always debates and nobody really agreed. And Dalton proposed it again, but with better scientific basis, but it was still totally controversial. And for 100 years, more than 100 years, it was controversial whether stuff is made of atoms or not. There were two sort of sides to the Earth. One were people called the holists. They thought that you just break things down and down and down, it's the same thing forever. And the other say, break it down and down and down, you'll get down to the little Lego blocks that everything is made of. So he and Dalton, and of course Dalton turned out to be right. But then around this time, people were thinking about this problem. They knew about the size, some sense of the size of the solar system, and there's planet Earth there alone in space. The sun's on one side, empty space on the other side, cold, empty space on the other side. And so it's heated on one side, cooling from the other. And what temperature would you expect the Earth to come out at when it's got the heat of the sun and the other? Of course, it's turning, so it nicely spreads the heat around. But what temperature would it be? Well, this is what the problem is like. It's we've got energy coming from the sun towards the Earth, and the Earth's getting hot. But we know that hot things give out heat, and people have known that for a long, long time. And so it's pretty straightforward. And people around that time, and one person who did this was Fourier, who I'll get to in my next slide, I think, and said, what temperature should the Earth be? And the result was that the Earth should be really pretty cold, icy cold, if it was just that simple picture. And then Fourier came along. It's 1829, the year of the Swan River settlement, and he was in France. And his question was, why isn't the Earth freezing cold? And he said, the atmosphere acts like the glass of a hothouse. So like the glass of a greenhouse, or like the windscreen of a car when you get into a hot car and it's stifling hot on a hot day when the heat has been trapped in there. And the way he put it, his words were, it retains the dark rays from the ground. And when I've talked to climate skeptics, and there's quite a few of them around, I've pointed out that if they've ever had an MRI scan or a CAT scan or any, or even used a tuner for a guitar or something, you're using Fourier's mathematics. And so he was right on all that stuff, and he was right here too. But these days there are fewer people you have to convince about that. But then the next person came along is Eunice Newton Foote. I wonder why she got the name Newton. I presume she must have had scientific parents or something like that. And it's well, maybe it's only her, it's her mother's family name or something. But anyhow, she did an experiment, and it's an experiment that Sean is getting ready to do for the for year 8 kids to do. So we're not proposing it at primary school, but it's a pretty simple experiment. It's just a bottle with some carbon dioxide inside it, which you can make by putting in some Alka-Seltzer or something. And you have a thermometer, but then you have another bottle that's just got ordinary air in it, no Alka-Seltzer to make the CO2, and you measure the temperature. She did this experiment in 1856. And she saw that the one with the CO2 got hotter. And she's largely forgotten by science, and it's a real shame, and it's a sign of this problem with women not being recognised for what they've done. And it's interesting, she wasn't allowed to present her results, but Professor John Henry presented the results for her at a conference, and he said, science was of no country and of no sex. The sphere of woman embraces not only the beautiful and the useful, but the true. So anyway, she found that basically, if you put CO2 in a tube, it got much hotter than if you just had air in it. But nobody knew why. But it was a few years later that people found out, and this was an Irishman working in Germany called John Tyndall in 1860. And he did an experiment and found that different gases absorb heat differently. Well, so had Foote, but he was only interested in what he called calorific rays, and calorific rays is what we call infrared these days. And in fact, the heat for his experiment was coming from a flask of boiling water. So he just had boiling water to make the heat. He was measuring the heat going down the tube, and he found that CO2 basically looks like black smoke in infrared wavelengths. He had a wonderful piece of apparatus, and Tyndall, I suspect Tyndall didn't know anything about what Foote had done, and Tyndall was totally astonished, and he said, that it was so transparent to light and yet so densely opaque to any kind of calorific rays. And those who have been taught about transparent gases will probably share my astonishment. To secure myself against error, I made several hundred experiments. So good science, you know. And so then we knew, and he didn't do it just with CO2, he did it with ethane, and all these gases had different sorts of names in those days. But so anyway, found that out. And then the next person who's really important in all this is the guy who calculated what CO2 in the atmosphere would do, what would happen if the CO2 increased. And he knew that in Europe there was 700 million tons of coal being burnt every year, which is tiny compared to how much is burnt every year now. But and he said what would happen if the CO2 in the atmosphere doubled, and he found that it would get 5 degrees hotter and more at the poles. His results are spot on, you know, compared with modern climate result. I mean, maybe not exactly spot on, but within a degree of many, many predictions. This is for doubling, and at that time, the CO2 concentrations were less than 300, I think maybe about 280. So it's about 560. We're at 412 today, 412.3, I think, today. But you have to keep changing these numbers every month or so because they're going up and up and up. So he did that very important calculation. And so we now got to the end of the 19th century. And around this time, atoms and molecules were still completely controversial. And many people thought that heat, like heat inside a piece of metal or something, was some calorific fluid that went in, and not jiggling atoms, which is what we know it is today. Until 1897, people thought that electricity was some sort of rays that they called cathode rays, and not a stream of electrons. And everyone said light was a wave, and it wasn't a stream of photons, because it was only in 1905 that Einstein found that out. And the warmth from a stove was calorific rays, and not, as we know now, infrared photons. So for some of you, the language I'm using is perhaps already pretty unfamiliar, like photons. Who feels uncomfortable with the idea of photons? No, none of you? But it's not really within the primary school curriculum. And what we think is absolutely shocking is that we can't teach kids at primary school about atoms and molecules and photons, because they explain everything. And we can't answer questions why unless we can use that language, because Einsteinian language, which we call it Einsteinian, that's just our label for it, because Einstein introduced the photon thing, has got so much explanatory power. And I want to give you a little sense of that. So out of all of this is this idea that we do have to look at the whole curriculum and be introducing the right language at the right age. We're teaching kids things about molecules and stuff with songs and plays, and we've been doing it in lots of schools. I tried to ask Jodie to ask her if she would sing one of the songs, but she said, no, I've got to do it. So but, just simple little songs like this one, which I can't sing well. I've got a really nice recording of it, but H2O, Mickey Mouse molecule, ears made of hydrogen. I love H2O. And we taught this to kids, and they, to 7-year-olds, 8-year-olds, and they love it. And they hear it once, and then they're singing it for ages, and they're learning the language, learning the idea that two oxygens and a hydrogen, two hydrogens and oxygen join together, and even the shape of the molecule. So anyway, carry on with the story because I'm going to run out of time. And so then came along Albert. This is Albert Einstein. At school, he was called the dopey one. That was his joke, a joke about him. He's an always wondering, dreamy kid. But he had lots of, he always had questions. He liked solving mysteries. And there were 3 mysteries at the time that he was interested in. And one was Brown's motion of pollen that he saw. Brown had seen the pollen through a microscope, and it wouldn't keep still. And this became known as Brownian motion. Nobody knew what caused it. The second was light, and the third was about speed, but that's relativity. We don't have to really worry about that here. So I'm not going to mention the third, but there is Brownian motion. Look through a microscope at pollen grains or other little particles, and it's always jiggling. It's not alive. What's happening, and this is what Einstein explained, was that the blue thing is the pollen grain and the other things are atoms. And the atoms are bouncing off it. Jiggling atoms are making this thing jiggle around. So we can see the thing jiggling around, can't see the atoms. And so, this was conclusive proof that stuff is made of atoms and heat is jiggling atoms. So that was a fantastic step forward. And today, can be on YouTube. It's only 2 minutes long, but I can't even afford those 2 minutes. So it's a lovely little movie. Oh, what's happened? There we go. So sorry to censor that movie for you because I love it, but it's so easy to find, and we show that to kids, and they all love it too. And it shows that the atoms are not some conceptual thing. Atoms are real. We can see them. You can find pictures anywhere on the internet. So that was that. And then same year, when he was working in the patent office in Switzerland, just doing this on the side, he proved that light comes as photons. What he showed is light can knock electrons out of metals, and that explained it was a mystery that had been found by Hertz, who was the discoverer of electromagnetic waves. But those waves are actually photons, and they're actually particles, but lots of them. And he explained that. But it was all pretty controversial at the time, and lots of people didn't believe him. But he won the Nobel Prize for it in 1922. And this is the physics behind solar panels. And solar panels are one of the big, important technological things for stopping the CO2 increasing. So it's of really enormous importance. But so photons are discovered in the context of light, visible light, but today we know that we have radio, infrared, visible light, ultraviolet light, X-rays and gamma rays. This is all this big spectrum of it. So how do we explain these things to kids? We do it with toy photons and toy electrons. One of the things we use is Nerf guns. like this to shoot Nerf gun bullets, which are little safe bullets, and all kids love. If kids know there's a lesson with Nerf guns in it, they're ecstatic. And we use the Nerf guns to shoot things like balloons and see the recoil when the Nerf gun bullet hits it. Now, that's not the whole story, but that's one of the things. We have a sort of toy photoelectric effect experiments, but we also have, and we have just over there in place, a solar panel that we use for making using photons to make our electricity, to do electricity experiments, to see that being turned into mechanical energy and things like that. And also LED lights, which is the photoelectric effect in reverse. Photon knocks out an electron and makes a voltage that you can use, put a voltage backwards. You can't do that. You can't take the power plug and connect it to your solar panels on your roof and have your roof suddenly start to glow. It doesn't work. But LEDs are still just using that physics in reverse, the energy of an electron converting into energies of photons. And we use toy solar cars and do experiments where you chase little tiny little solar cars around on the floor with a little laser pointer. A laser pointer can just send them around. Yeah.
So the green balloons are your pollen.
They could be my pollen.
And the Nerf gun bullets are your atoms.
That's one interpretation, because all these things, because they're all toys, I can interpret it in many different ways. This is an atom being hit by a photon, and we use that to teach kids the uncertainty principle, which says that when you measure something, you create a disturbance. And we photograph kids with Nerf guns, with Nerf gun bullets that stick to the wall or stick to a whiteboard, and have kids standing there and shoot all around. All these bullets sit there and leave their picture behind, which is another aspect of it. But I'm going to come to this, I'm talking about bullets, I'm going to come to this particularly important part of understanding photons that's pretty straightforward. But it relates to this battle when even people who proved that Einstein was right, they still said, but his interpretation must be completely wrong. There can't possibly be photons. Just because his experiment showed that doesn't mean that there were really photons. So it was very hard, a very difficult time for nearly 20 years until people accepted it. And part of the acceptance was somebody invented a good name, which was the name photon, because before that they called them energy quanta, and that's not a very friendly name. But then there was this guy de Broglie, a French Count Louis de Broglie, and he worked out that everything has bulletiness, which justifies why we use our Nerf gun bullets to be pretend photons, but everything also has waviness. And so somehow everything, atoms and molecules and photons of light, and even quite big things, big molecules, they all have this wavy property as well as a bullety property. So we have kids making toy photons like this. They've got some bulletiness, which is a lump of blue tack or something on the one end, and they've got some waviness as well. Now, this is all, in reality, it's all integrated like that. You can't even have a picture of a photon. So there's no such thing as a picture of a photon. So this is just a way of thinking about these two qualities they have. But waviness is a quality that allows things to cancel out. Waves can cancel each other out if they're in opposite directions. And bulletiness is this ability to hit things, to damage things. UV photons have got more bulletiness than red photons, so you can't get sunburnt under a red light, but you can get sunburnt under a UV light. They've got enough bulletiness to break our DNA, and of course gamma rays. And if I wanted to make this a highest energy gamma ray, this thing, if I started from this and pretended this was light, the highest energy gamma ray would have something that weighed 100 million tons at the end of it. So there are these incredible photons that have got enough energy. They say it's enough energy as a baseball traveling at 160 kilometers per hour, or 100 miles per hour. This is American, some American, so spread that. So this is really important understanding. But for us in climate change, we only really care about one thing, and that is the amount of bulletiness and waviness of infrared photons compared with the things they're going through, which is gas with CO2. So we have to then come to think a little bit about the molecules of CO2. So let's go to the next one. So yeah, so there are pipe cleaner photons, and we get kids to make them, and you see that the wavelength is short for a blue one. It's got a big blob of blue tag, and a red one has a little blob of blue tag and a longer wavelength. So that way kids get an intangible idea. We get kids to make their photons and then line up in a spectrum, you know, red to blue and things like that. But then, so then the question is, why is it that CO2 is so different from oxygen and nitrogen, which nearly all the atmosphere is made of? And as an experiment that I like doing, I've got a video of it here. I could have done this in front of you, but it would have taken too long. Hopefully, if I press this again, it'll go. And it's just a cup of water with a green laser pointer. I have one in my pocket, it's disappeared. Yeah, and now I just put in about 100 parts per million of milk into it, and I have a look at the laser beam going through, and I can see the laser beam only gets about halfway through the cup. And that was only 100 parts per million. So some things, that little bit of milk was enough to do it. If I put the same amount of sugar in there, it wouldn't have had any effect whatsoever. So, so some things absorb and some things don't. What's the reason that CO2 absorbs this heat and others don't? And if you have infrared cameras, you can see the CO2 plumes, and that's not like a dirty, smoky chimney. That's a perfectly clean chimney, but what's coming out of it is CO2, and it's hot CO2 that you can see with an infrared camera. And of course, NASA looks down on the Earth with infrared cameras to see how much the whole Earth is glowing in infrared, to be monitoring the extension of the, how the greenhouse effect is going. So, yeah, so, well, I'm just saying, so I'm saying that atoms and molecules and photons explain just about everything about climate change. And so you really need to be able to introduce that. And so why does CO2 absorb photons? Why is it like the milk and not like the sugar? And if photons are to be absorbed, there's two things they have to do. They have to match the waviness, and waviness means, something going like this, but it also means a frequency. And there are many, many ways you can see and understand how frequency matching lets energy transfer. I have a demo over here. I hope you can see it. It's actually pointing slightly the wrong direction for you to be able to see it. But it's super simple, and you can make this with, these things could be soft drink bottles or hanging there. Doesn't matter what, but this one's got ping pong balls. And they're all hanging off the string. And here is a pendulum, which is a little bit heavy. And I swing it back and forth. And now after a little while, you can see there's a bit of disturbance to the whole thing when I started it. But after a little while, you'll notice that there's only two pendulums swinging much. And they're the two that happen to be the same length as that pendulum, because they're swinging at about the same frequency. And these ones are sitting quite still, and those ones are sitting quite still. If I change the length of it, I haven't got time to do it, but if I change the length of it, I can make it so these ones all swing, or those ones all swing by making it as long as that one or as short as that one. So that's a very super simple experiment that kids can do to, thanks, Kyla. But there's another fun one, which I like, which is, it's just a wooden box with a tuning fork on it. Trouble is most primary schools probably don't have tuning forks, I don't know. But here's the box. And now if I put my hand here, at a certain distance away, I'm tuning this just like you might be tuning a trombone or a flute. I'm tuning this by just putting my hand there, and it gets much louder. Why it gets louder is that a lot more of the sound energy from here is getting out. And that's because I had matched the frequencies or matched the wavinesses of those two things so that the energy comes out. So that is, CO2 happens to have the right waviness for infrared photons. And but there's a second part to it, which is electrons must, Kyla, could we switch lights off? Yeah. But I'll probably want to find again in a little while. That the electrons, it turns out from the sort of theory of electricity, that electrons must move asymmetrically in their vibration. So this vibration that I did on the tuning fork, which I did by just putting my fingernails on both ends of it, was symmetric vibration. But and a molecule, and we put, so we have all these toy molecules like this, and these are just tennis balls with magnets inside them, and so they stick together quite nicely. You can measure the force of attraction. Magnetism is very similar to the forces of atoms, and but how can this vibrate? It can only vibrate symmetrically like that tuning fork. You can just go in and out like this. But I can't make photons connect to any vibration that's symmetric like that. They can only connect to something that's not symmetric. And to make it not symmetric, you've got to have three atoms. David Wood made me this CO2 molecule today. And it's just three balloons, really easy to make. You can do it with also tennis balls, but so there's an asymmetric vibration, a bit like that's supposed to be showing there. And that's the type of vibration that photons do connect to. So here's my big magnified CO2 molecule, and photons connect to that if they have the right waviness. That means the right frequency of vibration, and if they and if the molecule's got the right property. So you can say that you want molecules that vibrate not like this, but something like this, or it could be like this. I can't do it very well, but so Indian dancers do things like that. And which you can see is that sort of second type of vibration, head going back and forth between the two arms. And then you can absorb. So oxygen isn't absorbed by the infrared, but the CO2 does absorb it. So we can then go on and look at the story of a photon and where photons get made, which is in the sun, and how they get to the Earth. And so this is a pretty complicated, well, a little bit complicated story, because the photons start as super bullety photons inside the sun when in nuclear reactions, and we won't talk about that. But then they find their way over about 200,000 years, they find their way out of the sun. And every time they're doing collisions like this collision, you can see just here, and they're making new photons. And so all these, and the photons are losing energy until they get to the surface when it's about 5,800 degrees. And then they are launched on their way through empty space towards the Earth. We've got 8 minutes travel time, it's all compressed down. They come here and land on the Earth. Then what happens is, and they're absorbed. Most of them are absorbed. They're not absorbed by ice caps. They're not absorbed by glaciers, not absorbed by white roots. but they are absorbed by most things on the Earth. And so the Earth gets warmed up by all these photons from that. And then the warm Earth, just like a hot stove, is giving out infrared photons, which I've got as little white ones. And on their way out, they hit a carbon dioxide. And when they hit the carbon dioxide is part of the gas. And these atoms are not just sitting there nicely lined up. And I've got them a bit too lined up. They're randomly vibrating all over the place. And they absorb that photon and vibrate like this. And then they give out the photon and lose their vibration and give out that photon, but that can go in any direction. So all the photons are coming in one direction from the surface out towards space, and then they hit these things and go in all sorts of random directions. And so that means roughly, a third of them get out into space and the others don't. Only for certain wavelengths of infrared light though. How am I doing for time? Badly.
I think it's still a fair number to go. But,
yeah. Well, I'll
just
yeah.
maybe stick.
So next slide, I'm not. So that's the story, and that's basically the atomic reason for climate change.
Sorry, just moving the camera. If you hold up something, can you also hold it to the camera?
Oh, sorry. I think I might have finished with the demos. I'm not. All the text describing some of that is there, but I'm not going to show it to you. I'm not going to show you this, which is the importance of big numbers and teaching kids about big numbers and how we're doing it. If you want to hear about that, talk to Anastasia. She's got a fabulous program of teaching kids about big numbers. And then it comes to all the different colors of light. And we put that into things like spectra. Is anybody, when you all look at this, how many of you say, oh, that's really messy, I can't possibly understand? Hands up if you think that. I'm sure half of you do, or 3/4. Hands up if you think, oh no, I'm perfectly okay with it. You're not perfectly okay with it. You always have to ask the negative question to get to find out the truth. Well, so this is about all the intensity of different colors of light. And this part here is visible light. All this is infrared light. And then there's the light that is leaving the Earth. And this looks like that. This is all in the infrared band from 100 microns. That's 100 times less bullety than visible light, maybe 200 times. And down to about 5 times. But there's one particular thing in this. There's a huge hole in the middle, and that's where the CO2 is doing that. And show you just my little animation. This is the blanket of CO2. This is the main part of that blanket of CO2. And so some wavelengths get out perfectly all right. If you're a 12 or 13 micron photon, you'll get out of the Earth quite easily, and that's no problem. But all these ones around here are being absorbed. And other things do it too. So I talked about CO2, but there's methane, and there's nitrous oxide, and water vapor does it too. So all the things that have got 3 or 4 atoms in the molecule are the ones that do the absorbing. I'm not going to show you the next slide. But finally, how do trees help? And trees help because they feed on carbon dioxide. It's basically really simple. Carbon dioxide plus photons plus water makes glucose. And glucose is plant food and people food too. So trees help. But then how the blanket's getting thicker and thicker and thicker. And I've got lots of data. And some of you might like to, who's seen this graph before? It's the famous hockey stick graph. And this is the graph showing how CO2 in the atmosphere was sitting around 280 for a long, long time. And then now it's rocketing up and it's in this really scary position.
I used to be the next president of the United States. Yeah, that one.
Yeah, I wish it was. And then the flow of water into Perth dams getting less and less and less and less. And number of extreme heat days in Australia getting more and more and more and more over the years. What happens when ice melts? There's some really nice classroom activities you can do about this. If you have an ice block floating in a cup of water, when the ice block melts, does the cup get fuller? No. Doesn't. But if the ice block is held up by something and it melts, then of course it fills it up. And so if it's got floating ice, it's not so much of a problem, but if it's not floating ice, it's a big problem. That causes the sea level to go up. And this is all going on faster and faster than people predicted. And well, that's more sort of political. So why does sea level rise? And it's two things. The ones that we just talked about, the melting glaciers and ice caps and things. But the other is the expansion of water with temperature. And I did a little experiment this morning, which is just got a clear wine bottle. And you have to get the aluminium part off here so that you can see this part. And I filled it to the very top with water from the kettle. And as it cooled off, the water level went down and down and down and down. Had to do this with a glass bottle. Plastic bottles have big expansion, so their volume changes. Glass doesn't expand too much. So glass stays fairly constant. And so the height of the water here tells me the expansion of the water. And it's a big effect. Kids can measure that easily, just with a ruler. And you just have to, use a kettle, pour the water in, and do that experiment. Over there, you can see all the experiments we do with showing atoms, toy atoms, states of matter, solid, liquid, and gas. And the main thing is jiggling atoms need more space. And so that's why they get bigger. So that's the physics behind that. And so we get sea level rise. And here's a picture of a future map of Perth. I live just here. Good fishing grounds. So I'm sort of imagining sometime in the future these advertisements coming up. Oh, that's 15 meters. 15. Yeah, and it's the predictions are going up and up. So I say grandchildren. I'd say it's maybe great-grandchildren rather than grandchildren.
My husband is the founding president of the Les Moody Surf Club.
So the rest of it is about, I'm just going to talk about renewable energy, reflecting the sun's energy, show you just a few pictures of trying to save a glacier by covering it with white sheets, painting the roads in Los Angeles, painting them white to reflect heat back up, and of course Greek cities. And trees, planting trees, forests store, say 100 tons of CO2 per hectare. And you can turn carbon dioxide into rock. It's called CO2 mineralization. So there's lots of great things that can be done. And carbon farming, where you do things to keep carbon in there, or do things to stop livestock emitting methane. And I'm just trying to finish as quick as I can. And this is my last slide. And I just wanted to say, and we didn't do any sort of welcome to country, but this was my equivalent of that. For our Indigenous people learnt that they had to care for the country, and they had 60,000 years or something, however many tens of thousands of years, to learn that they needed to do that, today we've got to care for the whole planet, and this is our moral imperative, like it was for Aboriginal people. And so we need to teach our best understanding of the science of climate if we're going to do it. And you know, every child learned the laws about about how to preserve the land in all sorts of different things. And it was a moral imperative, and it was an unbearable trauma for them when white people came along and just violated all their land use rules. So modern science has brought us recognition of exactly the same thing, that we've got to care, but we now have to care for the whole planet. And so I think it's really important that every child learns about climate and the responsibility for caring for the planet. So thank you.
Now, while we switch over, if anyone's got any quick questions, don't.
Yes. The 15-metre sea level rise you mentioned, I know we came up last, we were about 2 metres deeper than we currently now are. We have sort of overshot before we came back. So we're 2 metres deeper. So I always in my mind thought, oh, we must be 2 metres. Where do you get the 15 metres?
Oh,
I'll show you a plot actually later in my talk.
Okay. Yeah. So I think the numbers are not that well known, but there are interesting underwater archaeology discoveries recently from up in the Pilbara, where we can see the effect of the sea level change. We know Aboriginal people were able to walk here from New Guinea, and so that's the other direction. So how far can we go? I flashed over a slide and didn't give you time, that where the data was 6 to 9 metres. So whether 15 is right or not, I don't know.
Yeah, I'll briefly show you some of the very similar numbers.
And we'll put the slides, I'm hoping, I'll ask Malcolm, but certainly David's slides will go on the website.
Right.
And I'll get the information around, when I send the information back about from your surveys and also the feedback that you give us here.
I know I'm happy to put up the slides as the PowerPoint exactly as they were, so that you can just use them, or you can edit them if you wanted to change them. And
if I import those slides into another PowerPoint, will the animation still work?
yeah, they were usually.
Can I just
Not always.
I'll just
I'm going to sit
introduce Malcolm very quickly. Malcolm's got this wonderful CV, but he doesn't include in it the most fundamental thing, in that he was initially trained as one of us as a teacher, and then got into academia and research and so on after that. But Malcolm is ARC Laureate Fellow, as well as Deputy Director of the ARC Centre of Excellence for Coral Reef Studies at UWA here, and has spent much of his life researching this kind of area, and is obviously very close to the impact of climate change on coral reefs, and basically wider than that. So over to you, Malcolm.
Right. So I should say I was a trainee teacher. Some of my best memories are being going as a young student to the primary schools and being preparing your lessons and having fantastic teachers actually giving you this sort of introduction to how to mix with students and so on. And at primary school was much better. I was actually a secondary school, and I like the primary school part of it much better because it seemed to have much closer kind of connections with the students.
Interesting how time makes you more fond about things.
No, but anyway, I won't continue my career. I'm just a humble country lad here.
He's not just a humble list or that. He's a fellow of the Royal Society, as well as a fellow of the Australian Academy of Sciences. He's maybe the most distinguished scientist in Western Australia.
I don't know. Thanks, Dave, for that. But anyway, one of the things we have been, I've been working a lot on the coral reefs. I'll give and we have just our Centre of Excellence that was an ARC funded. It was one of the longest running centres, 15 years. It just finished last year. These are only meant to run for 5-year intervals. So I'll give a bit of perspective about how climate change is affecting corals, because that's my kind of special interest. But what I'm going to try and do now is give you the more specifics about climate change, and And David's is fantastic introduction, because you've gone through and explained a lot of the basics that I'm going to just, assume now. I don't have to worry about that at all, and that's fantastic. So I'll show you what is really the basic thing, and you indicated this, David. This comes from an IPCC. This is going back 10,000 years, and you can see that CO2 is about 280 ppm, that very number. Actually, it does oscillate over longer timescales. If you go back 20,000 years, you'll find this is down at 180 ppm. So it does have that natural fluctuation. I'll explain why in a minute. But of course, we know now why it's rising up. So this is actually an old slide, but I'm not embarrassed about it. That's 2008. But things haven't changed much. If you just imagine these lines being projected up forward in time, we really have not decreased in any substantive way yet our burning of fossil fuels. So black is the coal, oil's perhaps gone down a little, natural gas has gone up, if anything, and all the others are still semi-trivial, right? So we've got along, we really haven't learned much in the last more than decade. But look at the shape of that curve, and I think, again, David showed, this is what we call the Keeling Curve, and this was Charles Keeling was at Scripps, and he started measurement of CO2 concentrations in around 1950. And what I'm showing is a little bit more detail, and I'll explain why in a minute. So you can see that this is 1960 actually, and the green is Mauna Loa, where you probably know about that observatory on Hawaii. But of course, from Scripps, he actually started at La Jolla, where some of the first measurements. The other place that I'm showing here deliberately is Point Barrow. This is Alaska. And at the same time, he had the foresight to measure samples from the South Pole. Now, in the meantime, Australians have got involved with measurements of CO2 at Cape Grim, which is in Tasmania. Now, there's some very interesting things, right? You notice that there's an oscillation in the Mauna Loa one, but by far the biggest oscillation, this is the orange curve now, is from Alaska, right? And actually La Jolla shows are very similar. So this is a seasonal change in CO2. But the interesting thing I want to point out is that the South Pole and Cape Grim, these are here, show almost no oscillations at all, almost a factor of 10 less than those in the Northern Hemisphere. Now, why is that? That gives us an important clue about how CO2 is being exchanged between the ocean and how it exchanges through the terrestrial biosphere. You'll notice there's some also interesting changes in slope, there's interesting changes in amplitude, and there's many, many papers written about these subtleties. But let's just worry about this a little. So what does it mean? Our planet is actually asymmetric. Most of the land mass is actually in the Northern Hemisphere. Most plants and vegetation is in the Northern Hemisphere. What we have in the Southern Hemisphere is mainly oceans. Although Australia is a big continent, in the scheme of things, it doesn't really matter. It's really the oceans that dominate. So what this tells us now is that we have two great engines, if you like, with CO2. And David mentioned this. We have photosynthesis taking up CO2, making plants. And this is occurring particularly in summer, right? So you draw down the CO2 in summer. And that's, if you go back, you'll find that's what happens. The CO2 is drawn down in the Northern Hemisphere summer, right? And it's a big, the other thing, of course, is that, that's why I'm here, is that these amplitudes, you can see it rising, right? And here is just the last 2 or 3 years, it's rising still, but it's much less than the seasonal amplitude. So that tells you immediately that when you go to this figure here, that it's taking up CO2 in a bit and then respiring it in the winter, releasing the CO2, and at night time as well. And so that's the atmosphere, natural atmosphere engine, and it's about a factor of order of magnitude bigger than what we're putting extra. I'll show that in the atmosphere from. And the other engine, of course, is the oceans. They're sucking up CO2 and they're also releasing it as well. Now, the difference is the size of these reservoirs and their speed. We know that this occurs on days to months, and the oceans are very much slower engine. This is how much carbon's in about. This, if you want to, this is about 10 to the 15. This unit, right? So there's 450 units of carbon here. Actually, in the deep oceans, you take all the oceans, about 40,000. So the oceans potentially. Let's go to the next slide now. So this is the natural system. 2 big engines, and they're kind of roughly in balance most of the time, right? Until mankind came into the picture, and we, instead of having all these nice forests and trees, we started doing land use changes. Initially, that was the major source of CO2, and then we started burning fossil fuels, right? And so that's added that perturbation into this natural system. Now, if the oceans were fast enough, they would be able to take it up and cope with it, but they're very, very slow reactors. The terrestrial biosphere is quite fast, but it's not that big, right? And actually, to store it, it has to go from vegetation into soils. That actually, vegetation to soils is a slow process. In the ocean, we're limited by the mixing of the surface oceans into the deep oceans, and that's,
so
the
that's just
slow
a physical water thing. You're not talking about things that live in the ocean taking up carbon.
No, they are. Both things are happening, right? But there's actually most of the carbon, I'll show you in a moment, another talk, there's a lot of dissolved inorganic carbon in the oceans, and that is still the major source of the major reservoir of oceans. But there's life is involved in part of this cycle, actually, in the oceans, as they are, as it is in the terrestrial biosphere. But there's both an inorganic and a biologic part to the oceans as well. And the inorganic is actually the dominant place where carbon's stored as carbonate, bicarbonate. Actually, it's just a simple bit of chemistry. It turns out, I won't try and prove this too. Actually, it's not hard to show that of all that's emitted, only about 45% ends up in the atmosphere. Roughly, these numbers are a bit rough. 30% goes in the oceans, and the other quarter ends up in the terrestrial biosphere. Now, you might say, well, how do you get this number here? Well, actually, it's pretty simple, as David hinted. We know accurately what's in the atmosphere, and then there's been estimates of how much has been burned, how much emissions, and that's not so accurate because you've got to figure out how much China burned in coal and so on and so on, what we did, and everyone's hiding their records. But now they're doing it better with satellites, right? They're trying to get that.
Yeah.
And this number has surprisingly stayed pretty constant as far as we can tell. So it looks like so far, and of course, it's hard to measure this number, the 25%, because the terrestrial biosphere is pretty heterogeneous. So it's hard to, you can do little experiments, but it's hard to get the big picture. Most of our best information comes from the oceans, and we do it by chemical means and other tricks, but it's still uncertain. So they usually say, well, we know that 45, that's 30, the difference will be what we think goes into the terrestrial biosphere. This has been a big controversy, actually. It's still, question. And of course, it goes to the point of where the vulnerability of our system is. We know, of course, if we start, and we are already, doing a lot of damage to the terrestrial biosphere, there's nothing particular why it should be up 25%. It could actually flip and be a source of CO2. If you start getting at the soils, releasing CO2, it can very easily flip from being a sink to a source. So this is the kind of, this is what we can do. I mean, obviously, over time, the oceans are going to take care of things, but none of us will be around to appreciate that.
You're especially talking about melting of the permafrost.
That's part of it. Yep. But
The offshore methane.
and there's methane clathrates, and anyway, there was evidence. I'm actually writing a paper at the moment that the permafrost in the northern hemisphere, where it's mostly located, we now have evidence that that's probably already turned into a source rather than a sink, right?
Yes.
And that's happening already. Right, so the thing is, the vegetation, this is a fast reacting, very sensitive and vulnerable. Oceans are large but slow reacting. And we know that from the southern hemisphere observations, we don't see these big seasonal cycles, just seeing this steady increase. And that's the slow engine of the oceans. By the way, the oceans are taking up over 90% of the heat as well, right? not only CO2 but heat. So that's why we have this problem, right? If the oceans were a fast reacting system, you probably wouldn't, but then we'd have very extreme climate, because the oceans are the moderator as well, right? They keep the whole planet stable, and it's that stability that we've, as humans, have kind of perturbed. Right, so I'm going to go through these things about ocean warming, acidification. This is the direct effect of CO2, and I'll talk about these rising sea levels that we've just had questions about.
What's more important, the phytoplankton growing or trees on land?
Phytoplankton in the ocean.
The oceans, yeah.
They're both important, but the trees are the very, the oceans, well, you have to go say, well, how is carbon partition in the oceans? It's mainly, as I say, I'll show you, it's mainly still the inorganic, right?
Okay.
Whereas in the terrestrial biosphere, we have trees, all other sorts of vegetation, and our soils.
But in terms of light, which makes a bigger impact to the drawdown carbon out of the atmosphere? The ocean?
It would be that I would no. Well, you have one's 25%, the other's 30%.
But you've got that chemical side of things in the 30% as well.
Yeah, right. So you'd have to say that vegetation, the 25%, is 100% virtually dependent on vegetation in the terrestrial biosphere. Whereas the ocean, you have both a biologic and it's called a biologic pump and an inorganic pump. You have two pumps in the oceans. I haven't gone into that detail in my talk, but yeah. But we'll come to that a little bit. And because of time, I'm not going to talk about, for example, ocean warming, we know causes lots of cyclone intensity, right? I'll talk about coral calcification. I'm not going to talk about the thermal expansion that David mentioned, but I will talk about this melting of the Antarctic ice sheets, because that is the sort of the big question mark, if you like. So there's some complementary, we didn't actually arrange all this. Anyway, this is the warming, this is an anomaly. The blue is, this is the mean temperature, and this is what, if you look, this is the rising temperature in the ocean. And it goes back, I think, to sometimes 1840 or 50. The point I want to make with this is that warming in the ocean is just not a straight line, right? It's not even a straight line on the terrestrial. It's marked by abrupt, what we call heat waves, marine heat waves. And you can see there's been quite a rise here at this point. And these heat waves are superimposed upon this increasing temperature. And 98 and 216, I'll point out some of those features. What happens when that goes on. 98, for example, we had warming right across the tropics of most of the world, actually. And this is an anomaly. So the red means that's additional warming compared to the baseline. And actually, so we had this part of Australia the waters got very warm. And as a result, we had a lot of what's called coral bleaching. I'm sure you've all also heard about this. So this is a coral that has its colours in its skin or in the living tissue, which makes the coral, and that they host symbionts. The technical word is zooxanthellae, which actually absorb sunlight and then transfer that sunlight into energy. So that's how corals get their energy from light. But unfortunately, they have this very strong temperature sensitivity that if it gets too hot, they expunge those symbionts, those zooxanthellae, and then they essentially lose their colour, lose their ability to feed, and all you have left is the bare white skeleton of a coral. Now you've heard
exactly a good evolutionary adaptation, is it?
In a normal, that's right, they're not adapted to climate change, right? And they're particularly not adapted that well to these very sharp spikes that we're on an already rising temperature. And part of
those spikes aren't global average.
No. These are mainly probably combined from El Nino events that they'll superimposed upon the. So they're an annual average temperature, right?
Yeah, but is it measured in one place or for the averaged over the whole of the world?
No, this is the global.
Yeah.
It's
amazing.
Yeah. It's actually though from January to December only, right? So it's not. I shouldn't say it's not the full 12 months. It's only the summer.
I see.
Yeah. So that actually that's the southern hemisphere summer. So that's why we're showing the southern hemisphere here, right? But it is a global southern, average for these months of the year.
Yeah.
So they're much warmer. During 98 was quite exceptional until we had, but remember we've been warming since then. So what was, but the corals, they wouldn't mind it if it was gradual rise all the time, but they don't like these sharp rises on already rising temperatures, if you like. So what happened in the 98 is that if you did it, this is a reef called Pandora Reef off the Great Barrier Reef. This is an aerial picture just flying on a plane. The whole reef turned white. That's all coral skeletons. And then they die, of course, right? They can't live without their tissues to feed with. The coral animal itself starves and dies. I mean, it depends on the intensity, what the mortality rate is. And you see these red areas along here is mostly in this 98 was in the inshore part of the GBR, and it actually tended to see go a bit more southwards from the central part. That was 98. That shook all the coral community quite a lot. And we've had other smaller events. And then in 2016, we had another big event, which you saw. And this shows the distribution. The red is all the bleaching occurred. And this shows the anomaly now at 10 degrees in the red. There's the 98 here. There's the 216. And this is the Kimberley. I'll come to that in a moment. Along the GBR, you notice it's much more in the northern part of GBR this time. And then you can see it, the red in the north. It was still present in the south, but not as relatively high a peak. And in WA, we didn't see much at all southwards in 216. So we had the green as non-bleaching. So the bleaching in 216 was in the northern part. And then since then, we've had more events. So events can be different intensities at different places, right? Not surprisingly, because it's a complex phenomena, how these marine heat waves, they're a combination of, well, obviously, what I use the word ENSO, it's El Nino, southern, there's this natural variability in heating of the north of waters in the Pacific, and how that interacts with overall warming of the tropical waters. So this is what we found, actually. This is records of our group's work in the Kimberley in 2016. And we went up there, and you see some of our students and postdocs looking at what we call the Intertidal Zone, because there's big tides in the Kimberley. And normally these corals are exposed. They sunbake in the reef because it's like 10-metre tides, right? And they're quite used to sunbaking and not bleaching. Yet the water's got so hot there that you can see all these corals here bleached, right? Even though they're adapted to being out of the water at times. And the subtidal ones actually bleach worse. You can see that a little bit here. These are the what we call the Acropora, which is the staghorn type, very sensitive corals. And then back to the indigenous people, we were working with rangers at this point, and we asked them, were there any knowledge from your elders about such an event occurring, corals turning white? And they said, we have no records in our history or our knowledge that this has ever occurred before. So in their memory, their history of events, this is quite unique. So whereas obviously that tells you that we're in a very unusual time. Acidification, that's actually the direct effects now of CO2, right? So here's our curve again. We've pushed up CO2, and I've already mentioned the oceans are taking up about 30% of the CO2. So 30% is being absorbed by the oceans, and it's got, I won't go through all this chemistry. It's actually pretty simple chemistry. It's fizzy drink chemistry, right? If you put CO2 into a fizzy drink, there's certain things kids know. If it warms up, CO2 is released. It actually absorbs more when it's colder. And there's a set of chemical reactions where you can actually release hydrogen ions. So the pH, you don't have to tell this is a negative log. The pH is as it's defined. But anyway, what it means is the the number of hydrogen ions increases. There's a general term called acidity, acid, right? Most people know what that is, sort of that feel for what that is. So the acidity increases. So this is why the word ocean acidification comes about, because as you take up the CO2, you're converting through this reaction. There's a bicarbonate change reacting with hydrogen ions. It actually consumes carbonate ion. Now, the reason why that is bad news is that very, very simple chemistry to make corals, to make calcium carbonate, you combine calcium and carbonate ions. And if what's happening with this ocean acidification is this concentration of this one has been reduced, of the carbonate ion, that's been reduced in the oceans due to the change in this equilibrium, the carbonate equilibrium. So when they get to high school, they can learn a bit more about the equilibrium, but it's not actually that it's something is very, very predictable. All the reactions are known exactly almost, and there's not really a question. It's just, really the only question is how much CO2 has been taken up. We know that's roughly about 30%. In fact, it's a buffering. This is a kind of buffer reaction that kind of helps the oceans take up CO2 to some extent. And as you know, actually, it turns out that, of course, as the oceans warm, that should, in theory, reduce the amount of CO2 uptake. But it turns out, if anyone asks you this question, the rate of increase of CO2 in the atmosphere far outweighs the effect of warming the ocean. So the loss of solubility from warming is far outweighed by the increase in concentration, right? So that's how it, that's how it works. And so we've done a lot of work on this actually, because if the carbonate ion, actually people have calculated it, I should say, this is doubling CO2. You can see the carbonate ion in particular, this is the number of ppms of it, would drop from over 220 down to 140, a big change, right? And if you took calcification as just that happening, you could say coral calcification could decrease by a factor of 2, right? If all this happened. But corals are a little bit smarter than many people thought. They have a way to adjust. I won't go into the detail of, they manipulate how they calcify, and they're able to actually adjust the carbonate ion concentration to some extent. And what we found from doing work on Rottnest Island corals, this is using mesocosms and other kind of methods, we found that this is the carbonate ion saturation. This is it's just the concentration, but the saturation is when it, if it's 1, it means it's just soluble. If it's greater than 1, then it's got it means that it's oversaturated, if you like, overcompensated, and it should be coming out of solution. So when things want to, so this is seawater. About this, corals, it turns out they manipulate their carbonate ion to help them calcify, and this natural process means that they're not quite so sensitive to the changing carbonate ion chemistry of the oceans as what we thought. But they still have sensitivity. It only gives them some partial protection. And so we've measured, for example, rates of growth of corals, changing some of these parameters. This is done in mesocosms, and so we.
What's a mesocosm?
This is it here. It's an aquaria, right, with controlled conditions where you can change the CO2 of the atmosphere, you can control the temperature and the amount of light and so on. So it's just like a fancy aquarium. We have a big one out at Waterman's, and we have corals growing in it to figure out all these experiments. It's a good thing to see. And so this is a kind of experimental thing. So what I'm saying is ocean acidification, you may have heard a lot about it. It's still serious, but at the moment it's not as serious as it potentially could have been without corals having this kind of ability to manipulate the conditions to some extent. So they have some natural resilience, if you like. Finally, let's go to this rising sea levels. What I like to do is show some examples from local examples. So actually, this is our curve. This is mostly thermal expansion from 1880 or something. 1850, I think. And you can see, there's been a steady rise in sea level. In fact, the blue shows what it is. And there's been some deviations, and this deviation actually turns from people building dams and things, right? The reservoir effect, you know, the dam effect. But you can go look, and this is our tide gauge from Fremantle. You see we've gone up over, this is in metres, we've gone about 0.2 of a metre up here since this tide gauge was set up in the 1900s. But you can, you know, your own experience, you might have, you know, Riverside Drive, there's the dotted, there's the road, there's the white, and you might remember those periods. They usually come together, I should say, there's oscillations in sea level due to tidal effects as well. But so there are periods when you get higher tides, of course, that together. And my favourite, I always go down and look at this tree just down here at Matilda Bay. And you might say to students, well, how does a tree grow out of the river? And what's happened, of course, is the river's been rising, right? And eroded. I don't know if you know this little spot here. You can see it at high tide. It's trees totally covered with water sometimes now. Yeah. So obviously this has major implications. You showed your first, you know, for 15 metres, but you can actually see these things happening now, right? So that's quite important. Just to give you the big picture, there are natural, what we call orbital forcing, and changes in sea level. So this comes from the Earth's spin axis relative to the sun, and in the northern hemisphere, when it's at that position, it will absorb. You'll get more sunlight directly. And the opposite happens on the opposite side, right? The southern hemisphere. Now, because most of the land is on the northern hemisphere, it's the massive. It's this how much of the northern hemisphere is absorbing sunlight that matters. Now, this spin axis is not constant, right? It's wobbling as well, and that wobble then changes on about a 40,000 year timescale, changes the amount of sunlight received in the northern hemisphere. It's called the orbital theory, or Milankovitch, some might have heard his name. And of course, there is a little bit of an effect in the orbit's not proper, you know, it's not, it changes with time as well on a long different time scale. So all these things are calculated by the astronomers very, very accurately, and you can actually predict quite a lot of this. And people are asking a question, well, what about, so the last time, so here we are today, the sea level up there. So we're fortunate in a way we're doing our experiment on a period of low ice. The Earth is relatively warm. It was, you can look back 125,000 years ago. It's my son looking at Rottnest Island Reef, and it's about 2 to 3 metres above sea level. Fair bit bluff this is, you might know that at Rottnest Island. And this is actually another outcrop at Ningaloo Reef. So WA has the best expanse of reefs, fossil reefs, about 3 metres above sea level. You know the seawater has to be above it, so you get 6 to 9 metres. And that's just a natural variability from the Earth's orbit. So we know that ice sheets can easily, and it's mostly an ice sheet driven thing, I'll show you that in a moment. By the way, when you had lots of ice, the sea level was much, much lower, right? This is about 120 metres, right? And so it's been oscillations as these orbits, these gives you some of the frequency of the orbits of this obliquity phenomena. And so we know we have this potential, right? We get to this point quite often, every 100,000 years roughly. And of course, it's mainly the Antarctic ice sheet that's the big driver in this thing. If you look at where ice sits in the Antarctic, black is minus 100 metres below sea level. These are all the large ice sheets, so big and heavy that they're sinking. Their base is below sea level, so they're sitting below sea level. And what happens, of course, if they start to melt, well, first they're pinned at the front at some point, but most of it sits below sea level. So this is a cross section. There's already satellite evidence for some meltwaters from gravity data. And what's happening, you get this sort of imagined water the ice sheet starting to melt, and you get these big cascades of water coming down, getting underneath. Once they get beneath this. And once this pitting point's released, you can suddenly go from grounded ice to floating ice, right? And that's exactly David's point. And, you know, how much? Well, we know easily 6 to 9 meters happens easily. If you melted a whole lot of this, you could easily get 40 meters. You know, so it depends on how much you melt as to the absolute. I mean, geologically, it's been a long, long time since we've melted all the ice, but we can certainly melt the equivalent of 10 meters of ice. Was not, we know that's happened in the past, the last time we went through this warming cycle. So that's the I use sea level, I'm a bit conservative, but greater than 4 meters are quite possible. And there's many features you can look around here that we know that's what happened last time we had the Earth naturally as warm as what we do now. And of course, there's many places, if you had, this is, I think, again, a 5 meters sea level rise, there's many low-lying, highly populated areas that would be cause a massive problem. Actually, Australia is, well, many of our cities are coastal, so we'd be quite lucky. And even here, we actually, there's this place is slightly higher, this little bench here, than if you go down 10 meters that way towards the river. You notice you walk down a thing, and that all this would be flooded, right, quite easily. Anyway, I just finish up with this is, you know, projections of where CO2 is. We spoke a little bit about this. So there's different cases now of this is where the path we're on. This is trying to keep the CO2 less than 450, and these are the temperature predictions for these two different pathways. And you probably hear on the news there's lots of effort trying to keep our warming below this. Well, they talk about below 1.5 degrees. I think, I'm sorry to say, that's unlikely to happen. But if we can try and keep it below 2 degrees, that, you know, that means we've got to reduce or stabilise emissions by 2050 to keep
Two to 3 is the real like danger zone, isn't it? If we push
above
3, we're done.
It's a matter of how done we're done. Right?
Well, it runs away if you can't do anything.
Well, people say 2 degrees is the runaway. I mean, it depends on the system, and the point is we don't actually know exactly.
Tipping point, sort of.
There are these tipping point phenomena, and there's a lot of cascade events that can happen, and we don't know very well what's going to happen in the Antarctic, right? You know, there's a lot of potentials, and so I just that's the story. Right?
Malcolm, can we go back to the corals?
Yep.
Looking at that time frame, natural oscillation of about 100,000 years.
Yep.
The species of corals, obviously, evolution is only goes so far to explain why we've still got corals that.
No, they actually move position, right?
As the sea levels change.
No, as the oceans warm, when you're in an ice age, you're compressing. You won't find the Great Barrier Reef present during an ice age. It becomes
a fringing reef, yeah.
It's a fringing reef in the tropics. So in Indonesia, you have these refugia where it's still quite warm during an ice age. And that's where corals kind of retreated to in that period when it was very cold. And then they've expanded as the temperatures have warmed. So we do see this expansion now. Rottnest Island is the case. Albany, some of the southern, we're starting to see slow expansion as the temperatures are warming. But of course, the problem we have now is we've got these heat wave events, which are quite serious. And of course, the acidification effect, right, does slow the expansion down. Whereas back in the last interglacial, we still were only at 280 ppm, right? So we didn't have the high CO2 in the last interglacial.
Excellent. Malcolm, thanks very much. Phenomenal talks, and as I said, we'll get them with the summaries and out. We've got about 20 minutes. That we had planned for this to be like a forum, and we said, well, how's a forum going to work in such a, we're originally thinking about the lecture theatre, and that's why we came up with the idea of asking the questions and sending the little surveys around, and thanks very, very much to all of you for putting your responses up. Kyla is going to share them with us very, very briefly in a moment, but what we'll do is, as I said, we will get both of the presentations and the summary of your responses and circulate it. And I don't know whether it was clear in the various communications that came, but essentially we're at the point with our Einstein-First initiative of writing the Year 6 curriculum resources. And we're very serious about getting some advice about from teachers like yourselves about what we can do and what we ought to be putting in that, because it seems to us that the electricity side really lends itself, the Year 6 electricity side really lends itself very much to the sustainable energy generation systems, and I think we can cover that off quite nicely. But we've also got that crazy little bit of chemistry that's mentions reversible and irreversible reactions, and we saw some fine examples of that in the talks, but how we actually simplify that so that it can be meaningful for kids at this age, on the assumption that they've been through our wonderful Einstein-First program and they've been exposed to atoms and molecules and photons and so on, leading up to this Year 6 level. But it's going to be, there's a little bit of a juggle that we have to do there. And then, of course, in Earth and Spaces, have I got the right name there? It's kind of, I think mostly you do volcanoes and earth process stuff, do you, at the moment? But there is a little thing that says something about climate, what's the wording? Who can remember?
Word climate's definitely not in there.
No, the climate. But there might be something about, but I figured that we could actually include some of this.
I've talked a lot about it with more the Year 5s.
Yeah,
okay. We have a lot of mixed year levels, so I start with a Year 5 unit, which you get to talk about the seasons and how they're created, so then you can talk about climate and then we'll go on to earthquakes and everything next term when I do the Year 6 unit.
Yeah, so
with the earthquakes, it was quite interesting to look at aerosols in the atmosphere.
Yes.
Because I talk about Mount Togo. I mean, this is all HASS stuff, so 4,000 years ago, the bottleneck, DNA bottleneck and all that sort of stuff, and the biggest volcanic eruption for the last 2 million years. So there's a whole lot of different tie-ins you can actually make. You can actually really get a lot of cross-referencing in different curricular areas. But with the aerosols, there's a great NASA thing you can actually search for. It's on YouTube. And they got different colours, which actually show the sulfates in the atmosphere. And you can actually see a volcanic eruption in Madagascar. You see that sulfate, but you actually see the sulfates in China. You see the sulfates in other places. You see fires burning on the east coast of Australia, and it's all in different colours. And so it's really interesting for kids to actually see over some months period about these aerosols in the atmosphere. You get the idea that this is where you get this.
I was going to say that same NASA side, I think, there's a CO2 showing how the the CO2 being emitted from the northern hemisphere gets distributed across the atmosphere. Right. You can kind of see it move. It's really quite. Nice.
There's a lot of curricular coverage in geography. There's a lot of repetition and duplication between science and geography. So you can access it through the geography.
So Dave, whose phone's just got running at the wrong time, we're actually looking to say, well, let's not develop this thing exclusively as a science resource, but actually think about it being a bit of an integrated kind of topic, so that we can actually pinch a bit of what's it called? HASS, pinch a bit of HASS time and pinch a bit of other time, so that we can actually do more justice to some of this stuff.
So there's a large cross-curricular element as well.
Sustainability, which really lends itself very much.
I just wanted to say that I did something with Year 1s today, which involved glass of water, light, milk. Refraction, the milk maybe looks blue. Why is the sky blue? Reflection of light. These are Year 1s. If I'd known that you're later than straight away, I would have been there. So you're talking about actually knowing what tools you've got available.
Yeah.
Throw in. So I throw lots of stuff in there about climate change, but it's not a climate change lesson. It's just, we're doing this, now think about it in terms of this.
So the point of that was that I've just given out now the very simple little evaluation that I hope you can spend while I just talk for another couple of minutes. And while Kyla scrolls through, we've got the information on the up on the screen of the responses. Could you just spend a few seconds? But the key thing is right at the end, turn over the page. There's a question 9. What was the best bit? Question 10, professional learning session. Do a question 11 now and say yes or no, whether you would like for us to continue to communicate with you about the development of these Year 6 resources. And we can get you informally commenting on ideas and so on. I think that would be a wonderful resource for us. I think that would be a fantastic thing from our perspective to get your real kind of input in at that level. So if you don't mind, if you have got a bit of time and an interest in this, if you just write your email and say yes, I would be like to be involved, that would be great if you could do that.
Yes, so David, so I just am wondering, like, how many teachers know about the Einstein-First Project and what we are doing? So because I can see some new students.
Yeah.
So just want to know, like, are you familiar with the project, with what we are doing?
No.
Maybe
So did we get the school brochures?
yes, it's
Yep, okay, so let's give those out. But let me see if I can have a go at this in a nutshell. Okay, so that's a very good, that's a very positive bit of feedback for us. In a nutshell, what we've done, and David kind of implied it in what he was talking about, is we haven't accepted the notion that we shouldn't be teaching kids about atoms and molecules and photons and phonons and so on, and that we're developing a curriculum. There's some other work going on in the early years, we'll talk about in a moment, but Year 3, we've got Atom Frenzy and Hot Stuff, and you can relate those to the 2 current chemistry modules. We've modelled the lessons a bit along the same kind of approach of primary connections. However, we've taken what I would call a less, if I can put it in the negative, a less literature-based approach. Okay, so that's sort of, we've got feedback that the science had sold out to the literature lobby a bit. Okay, so that was sort of where we're going with that one. In Year 5, we're introducing our May the forces be with you, the forces be with you. And the 2 forces that we introduced to the kids there are gravity at a very simple level, so thus getting into ultimately Einstein's gravity, but more importantly, electrical forces, which are of course the basis of all electrical and magnetic forces, and of course drive what happens in chemical reactions and how atoms and molecules form and combine and recombine, and all of the energies and so on that are associated with. So that's the kind of the bigger picture thing about Year 5. Year 6, we've got Year 5, we've got fantastic photons, which is, as the name implies, all about light, and the solar system one, that basically, so we do gravity. And then in Year 6, which is this little challenge that we're currently dealing with around how in the hell we can actually get all primary kids, because our ultimate aim is to get Einstein first infused right across all schools in Australia. So to influence what's happening with the car and SCASA and so on. And so that's sort of where we go. So Kyla, do you want to?
So just on that, Carrie had a question. She was asking, what about the changes that Cara is doing to the science curriculum and how are we factoring that?
Yeah, so Dave, do you want to answer that one?
Yeah, so I did completely hear what you said, but how are we dealing with? Is that what the word was?
What about the changes to Cara and how
I think yes. So we got a Cara involved when we first made the proposal for this and before we got funded. And then we've been sort of dealing with them. It's not, I can't say that it's all super easy, but middle of the year, they invited me to give a seminar to all of the curriculum groups that they have in every state. And they seem to be really taking our ideas very positively. There's always a couple of people who say, oh no, you've got to teach, you know, Newton's gravity first before you teach Einstein's and things like that. This really reflects the fact that that's what they did when they were teachers 30, 40 years ago.
Atoms because they can't be seen, so they're not concrete, because Piaget said they weren't concrete. And so there's all this kind of strange historical stuff.
But I think we're winning in a fairly big way.
All I know is that when I have thrown in at year 3 level or 2 or whatever, you know, CO2 or O2 or H2O, the kids, I've had kids who have gone off and they have learned the periodic table. You know, we come down so much.
Absolutely.
And so that's sort of where we are. And then that continues through into secondary. So the theory is that by the end of when all kids have been through this program, they all get to the end of year 10, we're not going to get any dumbass politicians standing up in Parliament saying that climate change. We will have an informed citizenry, because if you think about it, all of the science we teach kids up to year 10, none of it touches this modern, what I would call modern physics, chemistry-based world that is actually the real world in which we live. So that's kind of where we're going. I mean, do you want to add anything to that?
Well, I think we haven't got time, but you've got a brochure and we've got a pretty good, and one really good thing to read is some of the teachers' comments. There's a year 3 teachers' comment in that, and the year 7 teachers' comment about how much more rewarding it is to be teaching this stuff, and how much easier it is because the kids are so engaged and there's no behaviour problems, and that you can't distinguish between the kids with learning difficulties and the kids who are really bright kids. They're all equally engaged. So, and it's because we do everything with activities. And the hardest thing has been, I think, has been to try to not scare people off by saying we're teaching Einstein's physics, and then everybody thinks, oh, it's also complicated.
But the thing
maths.
is, when you teach anything like this, the kids ask questions and you go, I don't know the answer
and you
to
could
that.
be able to give them a satisfactory answer.
Yes, so you make sure you go away.
Here we
with
are,
something.
And
Sorry, when you say we, how do I've only
Yeah.
the day before yesterday.
So-
Is it something that you hand to us as teachers, you come into schools?
yeah, so we've got about 16 partner schools, and and the teachers come in here. We give them training workshops and things like you know, how to teach about atoms, and we've got a book of plays where the kids do role plays and songs.
And if I want to be involved in that, how do I get involved?
Okay. Well, that brochure that we're handing out, so we've actually got 2 brochures that are almost identical. One saying we need more money and give us some money, and the other one saying we need more partner schools, please. You're welcome to join as a
So
partner
it's not
school.
in a position to, it's not like primary connections where you get given the curriculum and you go.
No.
And
So, I mean, we're getting there. We've
Okay, but
got
that's
the
the ultimate
module.
aim.
That's the ultimate aim, and the ultimate aim, I mean, we shouldn't be saying this publicly, but we do anyway, is that we hope to be able to work with the academy and the people around primary connections to influence significantly primary connections so that we can, basically get this stuff as the mainstream work that everyone does across.
one of our big supporters is Lynn Beasley, who you might have come across. And she used to be the WS chief scientist. She's now taking on the role of coordinating the education side of the Academy of Sciences.
Oh, wow.
And we've been sort of plotting together how we go.
So there's a whole lot of stuff that you guys don't need to know about, but it's important that, I mean, Dave often says that, the discovery of gravity waves took 100 years and was an incredibly complex thing, but he doesn't think it's quite as complex as changing the curriculum. Look, can I introduce Jyoti, who is the coordinator. Jyoti did her PhD with David around a lot of the activities and the work, and is sort of the main one that's proven the viability of these kind of ideas. And I'll just ask Jyoti to say a few words, including about a couple of the handouts. And just a little thank you to Malcolm, just while Jody gets to the front. I've also put in there a very cheap little ad for STAWA to see if you can talk your boss into becoming a school member, and the benefits of this to be, I hope it's there, is it that little, yeah, the little short one, the benefits of the school membership. We understand, I mean, there's a whole change of, people don't seem to be becoming personal members of these kind of associations much longer, and so the question about the longer term viability of the associations, and this is the way we're going to try to see if we can keep them, the high level services coming back to schools to support the science teaching, particularly in primary schools. Jody.
Okay, so first of all, thank you everybody for coming, and thank you for Mark so for presenting a beautiful presentations. I hope you enjoyed both of the presentations. So join me to say thank you to David and Mark. I can send you a small gift from our team, so please accept it.
Oh, thank you.
Yeah.
Thank you very much.
Okay, yeah.
It's very enjoyable. It's a pleasure to be able to talk to you.
And Jody just mentioned that.
Yeah. So a couple of things for the Einstein-First project. So I can see from the list a few of schools are the partner of this project. For example, Orbital primary schools, and there are some new names on the list. So that's why I thought maybe I should tell you like what we are doing in this project. So this is our rooms, and you can, after the workshop, you feel free to see the room around, and you can see our beautiful posters, play with our activities. So if you would like to join, so first of all, I hope you will talk about this seminar to your kids, definitely. So like pass the knowledge to them, so because they are the future of our country. So I think it's really important to give them the best understanding of our universe. And second is like, if you want to join our project, you want to be a partner on this project. So talk to me after the session. So I will tell you like how we can move further from here. And so we just published our first book from this project, Teaching Einstein in Physics in Schools. And if you want to order this book, so talk to David Wood. So he's in charge of taking orders. So in this book, this book has been written by our international collaborators. So each chapter like tell about how to teach different ideas by using different approaches. For example, hand-on activities, online things. So yeah, so if you want to get this book, so talk to David Wood. And
I should say it's not like a complete like lesson manual. It's more like giving information at the level that school teachers need to be able to teach it, and primary school and high school, and including years 11 and 12. You know, there are a lot of people from around the world, you know, with different focus. Quite a few have a focus much more on senior school, but our focus is very much on years 3 to 10.
Yeah, and the last thing is, so visit our website www.einsteininphysics.com, and on the home page you will see a subscribe box. So subscribe to that so that you can get newsletters or updates from our site. And also like if you want to see the resources, so there is a tab called secure resources. So there's a password, and if the password is EFP, Einstein-First Project, 3 letters. So you can download the lesson plans, and then you can see like how our lesson plans look like. So each lesson has some activities. So feel free to do that. And also like if you want to talk more about this, so feel free to talk to me after the presentation.
And I'm going to have the last word. No one gets out that gate there. Elaine's going to make sure you don't. And you're going to come out this gate here, please. And you're going to give me your evaluation. Some person disappeared from there, I think it was. And I've got to try and work out.
Cups there, let's do the
She
was, I was chatting to her earlier.
Because I'll contact her and get the feedback. The feedback is really very important. And please tell us whether you want to be part of it, you know, part of the whole information thing, and particularly
it doesn't make our feedback anonymous, however.
It doesn't, but it's only because I'll be the only one that does the analysis. Anonymous means you won't be identified in the write-up. And Jody and I will write back to you as I said, probably in a couple of days with the summary of our feedback. Kerry and Alexa, if you're still with us, thanks so much for joining us. And I'll give you a little separate email just to talk to you about your response to the session, and I'll also send you the feedback sheet so we can get feedback from you as well. So thanks very much. I'll stop talking now. You start writing, and once you've finished writing, you may go home. Thank you. Thanks, Malcolm.